multivariable calculus, 15.8. We're on cylindrical coordinates. You can see we were working on example 3, and we were setting this up. We were changing everything, and very importantly, we went back to the XY plane here, and especially to get those R and theta boundaries. I just want to point something out very, very quickly from the beginning, that R and theta really are coming from that XY plane, just like you did in BC calculus, just like you did in single variable calculus. And then cylindrical coordinates just throw in a height right after that. So we've got this solid, and every point in this solid that we have here, every little point, like that red dot that I had and so forth, how do we get to it? Well, we'd go to the XY plane. Maybe you're not going to have to spin out a full a unit distance. That would be right on the edge of that cylinder. Maybe it's only at a half or at a third. You'll rotate a certain theta, and then you'll rise up so ever many units. Every point inside that solid could be represented by coordinates that way. Well, once you've set this up, my goodness, right now it just becomes a matter of just going through the mechanics and cleaning this up. Square root of R squared is R, and R times R is going to get you an R squared. So we're going to very quickly just work this out. So we'll have K R squared, and then we have to take our antiderivative with respect to Z. So we'll have a K R squared Z, and we'll be plugging in a 4 and a 1 minus R squared. And then we still have our double integral over here. And we just have to be patient and work this all out. So we'll have, this is 0 and 2 pi, this is 0 and 1, and we'll have a KR squared, and this is going to be a 4 minus 1 minus R squared, and as we distribute this negative, it'll be a minus 1 and a plus R squared. So this whole big expression inside is going to become a 3 plus R squared, right? It's going to become a 3 plus R squared. And then, of course, you'll have your K R squared out in front. So I'm going to continue this work up here. And we will have a 3 KR squared plus a K R to the 4th when we distribute that, okay? So now what? We just have to take our antiderivative with respect to R. We're going to bump that up to a 3 and divide by a 3. That'll be a KR cubed. This will become KR to the 5th, pardon me, all over a 5. And we're going to evaluate that between a 0 and a 1. So when we do that, when we plug in our 1, I think you can quickly see that you're actually just going to have a K plus K over 5 minus a 0. And that's going to be 6/5 K. So we're almost there. We're getting very close. Antiderivative will have 6/5 K theta, evaluating between 2 pi and 0. Once we plug that 2 pi in, we'll have 6 times 2 pi, which is 12 pi. Of course, you plug in your 0, and you don't have anything. But that's your mass. That's the mass that you'd wind up with. So that's our preliminary work for a problem like that. This problem could have been done entirely in rectangular coordinates. Now it would be more difficult because as you solve, you'll have all those radicals and so forth, and it gets rather messy. speaking of what it would look like if you were solving in rectangular, it would look something entirely like this. Last problem, look at example 4 here, and you can think, oh my gosh, wow, all these radicals, and wow, you might ask yourself, is there an easier way to avoid all these square roots? And of course, you can immediately begin to say, well, wait a minute, maybe polars will help us out, and in particular, if we were to work out cylindrical coordinates, we could get some help. Obviously, an x squared plus y squared equals r squared, and that certainly is looking very, very promising right here. It's also looking very promising in our integrand, isn't it? But I do want to point out to you, even furthermore, as we're looking at our boundaries for x and for y, and remember, that's always going to relate to a double integral over an area. As we're looking at this, you can think, well, y would be between these two curves here. And guys, I hope you can quickly see that these are equations of circles. As you're looking at that, it'd be x squared plus y squared equals 4, meaning that your radius would be a 2. Remember, it's always r squared right there, and our confirmation for dx would be going between x equals -2 to +2 there. So, wow, you begin to look at that, and you just see circles everywhere here, and cylindrical coordinates are definitely what you want to do. So, look, in our integrand, x squared plus y squared, well, that's r squared. We're going to change our differentials and say, you know what, we're going to go to an r dz dr d theta. And right here, we're going to still have a z value at 2 for our upper bound, but this thing becomes the square root of r squared, which is just an r. And then our dr, well, you can see our radius will go between 0 and 2. How about d theta? Well, we're going to go between 0 and 2 pi. And it's only going to take us a moment now then to clean this all up. And let's do that. So we'll have between 0 and 2 pi. Here's 0 and 2. Here's an r and a 2. This is r cubed. And now we'll just go step by step. We'll say, hey, let's take care of this thing right here. Antiderivative is going to be r cubed z, evaluating that between r and a 2. And as we do that, as we use that fundamental theorem, we'll have our r cubed out here. This would become 2 minus an r. And we can clean that up rather quickly. As we distribute, this will be 2r cubed minus r to the 4th. And you can see things are going rather smoothly. We can get this worked out pretty quick. So now what? Well, antiderivative, bump this up. This becomes r to the 4th. Divide by 4. You'll wind up with r to the 4th over 2. Double check that you're right by taking a derivative. This becomes r to the 5th all over 5. We're going to evaluate that between 0 and 2. And when you do that, you'll get a 2 to the 4th, which is 16. That's 16 over 2. That's an 8. Minus 2 to the 5th, which is 32. That's 32 over 5. And we'd say minus a 0. Well, we're getting there. We're super, super close. If we have 8 minus 32 over 5, that's really like 40 over 5 minus 32 over 5. And you should get 8/5 then. So we're almost done, on the cusp of finishing this up. Antiderivative, you'd have 8/5 theta, evaluated between 0 and 2 pi. Guys, when you plug in that 2 pi, I hope you can see you'll wind up with a final answer of 16 pi over 5.